Hello and welcome to this clip going through Cambridge Chemistry Challenge from 2017. It's one of a series of clips I'm doing, working my way through this paper, starting with question number 1. In each clip what I'll do is I'll look at some of the advice that it gives you on the front of the paper, because it's obviously worth considering that the Cambridge Chemistry Challenge is definitely meant to be more challenging, but it's also designed to be quite deductive. So in a slightly ironic twist, they don't actually need much revision, but that doesn't mean you ignore it either. So the best way to prepare for a Cambridge Chemistry Challenge paper is to maybe try a couple from their website, but consider some of the strategies you might want to consider whilst you're doing the paper. So like it suggests in their advice box, expect to see things you haven't seen before. So the way to do it is to apply your logic and current knowledge to find your way in. So the important thing is to try and be resilient. It's going to get tough in places, so don't give up when that happens. So the way to get your head around that challenge is being willing to move on and come back to the difficult parts a bit later, when your mind's had a chance to think about them subconsciously. So when you're looking at the other parts of the cover for the advice, remember to lay out your calculations stepwise. So it's also essential to make sure you're taking care with units and significant figures. Obviously it's easily forgotten in the pressure of an exam, but try to remember always to check your units and significant figures that they match what the question is asking for. So the C3L6 paper will give you a periodic table. So what you need to do is actually use the data on that periodic table, not relative atomic masses that you may have recalled from your particular exam board's periodic table. So stick with the data you're given, otherwise your calculation will start to go outside the range required. So let's have a look at question 1. At this point it's really worth having a copy of the paper downloaded and printed out while the clip is playing. So to get access to the paper, you'll need to go to www.c3l6.com and click on Lower 6 Competition button, and you'll be able to access all of the past papers and mark schemes and examiners' reports from there. So from this point onwards, I'm assuming you've got the paper in front of you. Can I ask that you turn to the periodic table? So you'll need to go to the back of the question booklet to find it. So part A says, write down the electron configuration of manganese in terms of its subshells. So this means using 1s2, 2s2, etc. So looking at the periodic table that's provided, you can see that the atomic number, which is the same as the number of protons, is at 25. So that gives us that electron configuration. And you can do a quick check as well. If you take all of the superscript numbers, which represent the number of electrons in each of those orbitals and subshells, it should add up to 25, which is the same as the atomic number, which is the same as the number of protons. So this is still fairly simple first-year chemistry if we're moving on to part B. It's successive ionization energies. So this idea is quite common to many C3L6 papers. The opening question will normally be something that you can relate to quite easily from your A-level work. This is to get you started and settled before they start moving on to more challenging material later on. So as you can probably remember, where there's a jump in ionization energy will signify where electrons are now being removed from a newer shell closer to the nucleus. So all the ionizations that are being ringed in blue represent outer electrons being removed. And as you can probably work out, there are 7 of them. So that means you could write down that the maximum oxidation number for manganese is +7. So to justify your answer like it asks you to, there's a large increase from ionization 7 to 8. So making a bit more space for further justification, this would mean that all the electrons are now removed from 3D and 4s. So further removal of electrons from shells closer to the nucleus would require much more energy, so it's unlikely that the oxidation number would go any higher. So looking at part C, it says that the MnO4- oxyanion It says that also covalent bonds between manganese and oxygen. So for the purposes of A-level, an oxyanion is simply a negatively charged ion which has oxygen covalently bonded to at least one other atom. So just to put it into context, there's some common examples that you might come across during your A-level course. Sulfate 6, nitrate 5, sulfate 4 and nitrate 3. Not forgetting, of course, that the Roman numerals in curved brackets refer to the oxidation number of the sulfur or the nitrogen. So if we look at the rest of the first sentence, it also says that manganese is covalently bonded to oxygen. This may challenge assumptions that you may have from GCSE. It's not uncommon to see this, but it's not talked about in the specification at A-level in any great detail. So, first question, or first part of it, asks you to draw a dot and cross diagram to illustrate the bonding in the MnO4- ion. So your dot cross diagram must have 8 electrons in each oxygen atom's outer shell in order for it to work and be balanced. The extra electron that obviously is in place because there's a negative charge overall of 1- should be on one of the oxygens because they're at the edge of the ion structure. So in crude terms, it shouldn't be on the manganese because this is tucked inside the 3D structure of the oxyanion. So any gained electrons are not likely to find their way inside that part of the ion. They'll be in the outer shell of one of the oxygens on the outside of the ion. So starting with the oxygens because they're more familiar atoms. So I've given each oxygen 2 lone pairs, so now I need to try and work out how to account for the other 2 electrons in each oxygen's case. So I can start paying attention to the manganese now. So looking at the periodic table again, you'll see that it's in the D block. So if it's got an electronic configuration ending in D5, because you worked that out earlier, that must mean that there's space for 5 more electrons, because the D subshell can take up to 10 electrons, including the 5 that manganese already has. So I can take 4 out of those 5 electrons and distribute them evenly. So in order for the oxygen atom's final 2 electrons, in other words, each one has 6, in order for that to be taken account of, and for the oxygen to now have 8 electrons in its outer shell, I need to create 3 double bonds. So in other words, I've filled up the octet in 3 of the oxygen atoms. So at the same time, manganese is now using all 7 of its electrons, or should I say outer electrons, and in doing so has expanded its octet. You'll notice that there are actually quite a lot of electrons now in that outer shell. So there's 7 of manganese own electrons plus the oxygen electrons. So the oxygens have parked their electrons in the subshell, in the outer shell of the manganese. So this D subshell allows that to happen. So we still haven't quite finished because we need to think quite carefully about how to deal with the extra electron. So I've added this to the 4th oxygen. So this means it can get away with having a single covalent bond with manganese. So don't forget, of course, it's a charged species, so you need your square brackets and the negative charge. So the final part of question C asks us to consider a bond angle in MnO4-. So in valence shell electron pair repulsion via CPR theory, you'll remember that double bonds are treated as one bonded pair, and not 2 bonded pairs. So we have 4 bonded pairs and no lone pairs on the central atom. So this makes our bond angle 109.5 degrees. So part D asks you to now consider writing a balanced equation for the reaction that they've described. But it says consider the oxidation states. So remembering the oxidation number rules, oxidation states must add up to 0 in neutral species. So you need to do something called balancing the equation using oxidation numbers. I'll take you through this in a second. So It says that KMnO4 is produced industrially from the mineral pyrolusite, a naturally occurring source of manganese 4 oxide. So reading the question, it tells me that it reacts with potassium hydroxide in the presence of air. Now, in the presence of air almost invariably means that oxygen is involved somewhere. So I'm taking a bit of an assumption and making a jump here and assuming that O2 is one of my reactants. So something you need to spot in the question as well. And the final manganese-containing product, potassium manganate 6, means that the manganese in this oxyanion has an oxidation number of +6. You've got to be very careful because we've been talking about manganate 7. This is manganate 6. And it also says there's one of the products, so I need to leave a bit of space to put something in there. So I'm going to start now assigning my oxidation states. Manganese 4 means +4, manganate 6 means +6 for my manganese. Potassium will only ever be +1 because it's a group 1 metal. So while we're there, notice I've put 2 potassiums into K2MnO4 to make that product neutral overall. So looking at the oxidation number changes, oxygen is reduced from oxidation state 0 in oxygen gas to -2 in MnO4 2- once. And manganese is oxidized from +4 to +6. Now each of these processes requires 2 electrons to occur, so they can occur in a 1-to-1 ratio. So the problem we've got is we're not balanced for potassium. There's 2 potassiums on the right-hand side and there's 1 on the left. So we get around that problem by doubling the number of potassium hydroxides. So once we've done that, we just have to check how many oxygens on the left-hand side, 6, how many oxygens on the right-hand side, 4. Now to take care of that, we can put in water. That gives us 5 oxygens on the right-hand side, 6 oxygens on the left-hand side. We are now balanced for hydrogen, so the only thing left to do is to look at how we can possibly balance for oxygen. So the O2 is where we can look, because the O2 isn't bonded to anything else. So the O2 on the left-hand side as a reactant is what we can play with. So basically, to finish this one off, all we have to do is instead of having a whole O2 molecule, you can put a half O2. So that now means we've got 5 oxygens on the left, 5 oxygens on the right. So, starting with part E, it gives us some information about what happens next. The potassium manganate 6 is dissolved in a solution of potassium hydroxide and converted into potassium manganate 7, our final product, by a process known as electrolytic oxidation. It also says that water is reduced to hydrogen gas, so this suggests strongly that we're dealing with redox. So let's take the oxidation part first. So manganese goes from +6 to +7, which means it loses 1 electron. And water, changing to hydrogen gas, is going to be H2O going to H2, like that. So that would involve the gain of 2 electrons. So to make that work, it has to have OH- coming off as a side product. So I need to slightly adjust my balancing of my equation. So I'm going to remove one of the hydrogen molecules. So if we take the MnO4 2- to MnO4- process, the oxidation first of all, and pop that about halfway down the page, that'll allow us to look at how many electrons we're dealing with. So before we do that, let's just mention that the potassiums can be cancelled out because they're spectator ions. So if we just stick to our 2 ions at the moment, that means there's 1 electron lost Therefore, for that to support the gaining of 2 electrons by water, it's got to happen twice. So therefore, what we need to do is to balance the equation accordingly so we can actually cancel out the electrons. So what we do is we double up everything on the oxidation, so 2 lots of MnO4 2-, 2 lots of MnO4-, and 2 electrons. So therefore the 2 electrons can cancel each other out now. So we collect our reactants from the left and our products on the right, making sure that any ions are now converted into their full species, because the equation in part 3 is what they're asking for, not just an ionic equation. So MnO4 2- now becomes K2MnO4 again. MnO4- becomes KMnO4, and OH- becomes KOH. So that gives us our overall balanced equation. So it says at neutral pH, the substance disproportionates. It says it's only stable at high pH. So high pH is in the presence of OH-. So neutral pH must be in the presence of water. So because it's a disproportionation, the manganese can't just be reduced to +4, it must also be oxidized. So the other species that we know of is the manganate 7. So in other words, what we're talking about is another product that contains manganese, is potassium manganate 7. However, we're not balanced for manganese. There's 3 on the right and there's 1 on the left. But that creates another problem. We now have 6 potassiums on the left-hand side and 2 potassiums on the right-hand side. And we're also a bit stuck because we can't keep changing the balancing numbers for the manganese-containing species. They've now been sorted out. So what we've got to do is consider that the potassium, the remaining potassiums, are found as ions. Now clearly the potassium ions can't just float around by themselves. There must be a cation, an anion of some kind that they are balanced out with. So an obvious candidate might be OH-. So for this to work, you'd have to double the waters on the left-hand side. So the next part of the question is much harder, section 2, but you'll notice they give you some information before they start asking you questions. That's because this part is well beyond A level, so this is the deductive bit. So the question is asking you for the units of the molar absorptivity, which is written like a little E. It's not E, it's actually one of the Greek letters, but I'm just going to call it E for now because it's easier. So, if there's no units, then multiplying all the units together must give you 1. So to isolate the units of E, you divide 1 over moles per decimeter to the -3 times centimeters. And by inversing your indices, you can get moles to the -1, decimeter to the 3, centimeter to the -1. So we can calculate the value for the molar absorptivity of potassium manganate 7 at 530 nanometers by just using the calibration curve, or the calibration graph as it should be called, I guess. So you can get A and C from the graph by just using the y and x coordinates for one of the points. So I'm making an approximation that the y coordinates are around 0.23. So that gives me a value of 2,300, obviously not forgetting my units like we talked about earlier. So with this next part, you've got to convert the concentration unit that you've been given into a concentration unit you can use, i.e. moles per decimeter to the -3. So if you remember that grams per decimeter to the -3 divided by mR is moles per decimeter to the minus 3, then milligrams, which is a thousandth of a gram, you need to divide that by 1,000 to convert into grams per decimeter to the minus 3, then divide it by the MR. So don't forget that to work out the MR, you need to use the periodic table provided. We're working with KMnO4. So that ends up as 158.034. So that gives us our concentration of 3.16 times 10 to the minus 7. So that gives us 7.3 times 10 to the minus 4. I'm applying two significant figures because the piece of data was in two significant figures for part I. So in part J, they want you to work out the concentration, but they give you the value for the absorbance. So what you've got to do is obviously rearrange. So they want the concentration in, let's say, in milligrams per decimeter to the minus 3. So that means you multiply moles per decimeter to the minus 3 by MR to get grams per decimeter to the minus 3, multiplying that by 1,000 to get milligrams per decimeter to the minus 3. So working that out gives us 27.48 milligrams per decimeter to the minus 3 as our concentration. Finally, for a 75 kilogram person, the toxic dose will be 75 grams, because it says 1 gram per kilogram of body weight. So what we do here is we need to take our concentration that we've just worked out, and bear in mind that it's for milligrams per decimeter to the minus 3. So we convert that into grams per decimeter to the minus 3 and divide 75 by that value to give us 2,700 litres to two significant figures. So this part is a bit easier because of the level of challenge in the previous part was quite high. So it shouldn't be too difficult to follow the simple empirical formula calculation that it asks you to do when you're determining the molecular formula. So when we're constructing our equation, we can have a stab at doing the state symbols because we know that concentrated H2SO4 has an L next to it for liquid. We know that KMnO4 is an aqueous ionic solution, and Mn2O7 is covalent because it says a molecule of compound X. So it's less likely to be solid because it's only London forces in action. Now obviously we need to make sure that we have balancing for manganese. So we add a 2 in front of KMnO4, and the only spare molecule we can think of, which would be sensible as another product, would be water. Now in attempting to do a structure for a molecule of compound X, we know that manganese bonds covalently to oxygen. It's unlikely to bond covalently to itself because it's metal. So we need to have a think about how we might do this. We've got 2 manganese and 7 oxygens. So we can start by putting an oxygen bridge between 2 manganese atoms. And obviously we've got 6 oxygen atoms left to use up. So we end up with something like that. So part L is also staying with more straightforward concepts from your first year. It's an enthalpy calculation. So what we've got to do is work out the enthalpy change of reaction for the decomposition of 1 mole of compound X. So as it says, the decomposition gives MnO2 and O2 as the sole products. So if you look at it, it says that compound X is in solid form in this particular case. So let's have a look at what would happen. So because we've been given delta FH data, we need to do a Hess cycle that involves the formation of our compounds. So we put the values in. Obviously for oxygen it's going to be 0. So we need to do the quick calculation for the others. I nearly forgot, didn't I, to balance it out. So that gives us a value of minus 298 kilojoules per mole to the minus 1. So next it's a yield calculation. So 77% is going to be the actual number of moles of carboxylic acid over the theoretical number of moles times 100. So what we've got to do is work backwards through the question. So it tells you there's a 10% excess of KMnO4, but that you're trying to make 300 grams of heptanoic acid. So the theoretical amount of moles is 300 over the MR. So that gives us 2.304 moles. Now working backwards through the equation, the mole ratio of heptanoic acid to heptanal is 1 to 1, or 3 to 3 as you can see printed there. So what you've got to do now is to bear in mind with a 77% yield, that's actually going to be 2.993 moles of heptanal required to make 2.304 moles of heptanoic acid. I'm just going to clear the screen to continue the calculation. So going back further to work out the number of moles of KMnO4, it's a 2 to 3 ratio, and don't forget you've got a 10% excess as in the question. So that actually gives us a new value for the number of moles of KMnO4. And to get the mass of KMnO4, you simply multiply that number of moles times the MR, which I make out to be 346.7893 grams. So the next part asks you to compare the costing of this particular process with the equivalent using sodium permanganate, sodium manganate 7, NaMnO4. So they're asking you how many times more expensive it would be to carry out the oxidation of heptanal using that rather than the potassium equivalent. So the way to start this is to work out how many moles of KMnO4 are in 1 kilogram, and then work out the cost per mole. So working with the NaMnO4, you can assume that that's actually about 500 grams, because the 1 gram of aqueous solution is roughly equivalent to 1 milliliter. So considering it was 40% by mass, that's 200 grams of NaMnO4 present. So the number of moles of sodium manganate 7, beg your pardon, is 200 over its MR, which is 141.95, equals 1.41 moles. So dividing the cost by the number of moles gives us 48.0851 pounds per mole for sodium manganate 7.